So we're about to start this unit about electric potential in Physics 40S, and I think it'd be a good time just to stop and talk a little bit about energy. So I'm going to find a little spot here in our notes. This might be a good place where it says more space for discussion notes, and I want to talk for a moment about work. How does work work? Quite often when we talk about work, we use the LOL diagram. The first step, here I'm going to do something, I'll look on the right here, of a 1 kilogram box that we are going to elevate. Let's say we're going to elevate it 2 meters. So it starts off here, and then a little bit later on it's up here, and we'll say that we've moved it up 2 meters. Well, when we analyze the work, first of all, we have to say what is in our system and what's outside of our system. So I'll, draw a little dashed line to say, what are all the things in the system. So in this case, and I'll write inside here that what's in the system is the box, the Earth in this case, and really that's about it. So we're going to elevate it. Something that's outside the system in this case will be me, because I will be the person elevating the box. So if we say to begin with, how much energy is in the box? Oh, here we'll even describe the event as Mr. Speiser lifts a box. And so at the beginning, let's say it's not moving, and at the end it's not moving. Let's just keep it real simple. So what kind of energy do we have to begin with? Well, we have Eg. We have gravitational potential energy, and that's why I put the Earth in there and the box, because we need to have both of those. And let's say that this is our zero level to begin with. So to begin with, we have no gravitational potential energy. And then at the end, we do have some gravitational potential energy. How much would we have? Well, Eg is equal to our mass times the gravitational constant field strength, which let's call it 10 newtons per kilogram, times the height that we have here. So this would work out to, gravitational newtons per kilogram. Oops. Okay, so this would be, what would be 1 kilogram multiplied by 10 newtons per kilogram, the field strength, multiplied by the height of 2 meters. Some units would cancel out, and we would get 20 Newton meters, which is the same thing as Newton meters is the same thing as joules here. So we're going to get 20 joules afterwards of energy. So over here, I'm going to write it as 20. I don't know. How about there? We got 1, 2, 3. I'll make 4 boxes, and we'll say this is 20 joules. So the way we think about work is then work must have been added to the system. So it was Mr. Speiser that did the work, and I'll try to make it look like 4 boxes here. 1, 2, 3, 4 boxes of energy were added, work was added to the system. Okay, so that's pretty straightforward. The stuff I wanted to remind you of then is that work, our definition of work is energy added or actually taken away. We can have negative work or taken away to a system. Another way of writing this is to say Eg initial, so maybe put an I there, plus the amount of work we did is equal to EGF. So in other words, work can be thought of as the final, if I subtract Eg initial from each side, it would be EGF minus EGI, or more simply now, then we could say work is equal to the change. Now I'm going to leave out the G in this case because it's really just the change in energy of all the energies there. So here, this is a standard way of kind of looking at work is work is equal to the change in energy. Maybe a better way to put in that equal sign is we could say the work is the thing that causes this change in energy because I added some energy. So work is when an external force comes in and adds. Now the part that I really wanted to remind you of is that when we look, if we look carefully at this work, we're going to see that work is always going to be equal to some external force. In this case, it was the force of Mr. Speiser multiplied by some distance. So let's analyze this situation one more time, and let's try to make it as simple as possible. So here I had, let's look at the forces of this box. So to begin with, it was lying there, and there was definitely a force of gravity downwards. What did I say it was? It was a 1 kilogram box, so this is 10 newtons downwards. And maybe it's on Mr. Speiser's hand. I'm not sure. So, here's a force of Mr. Speiser here. Force, I'm just going to say external in this case. And if we try to make it as simple as possible, let's say it was moving at a constant velocity the whole time. So then it started here, right, and it ended up here for 2 meters. So it ends up over here. And we still have this force of gravity here, and we have this external force, right? So I'm not too interested in the force of gravity here, but the biggest thing I'm looking at, so I'll just erase it here. The biggest thing I'm looking at is this force acted for 2 meters. This force must have been the same as the force of gravity if I was going at a constant velocity. So in other words, it would be 20 newtons. So here we see 20 newtons times 2 meters. So that would have been our 40 newton meters, which is the same thing as 40 joules. Okay, so it's the same idea we had before. Oh, did I make a mistake here? Yeah, I made a mistake. This was 1 kilogram, so this would have been 10 newtons here. And this would have been 10 newtons here. So we get the same 20 joules. Okay. All right, so that's the point I wanted to make, is that when we look at work, we can also look at it through this lens. We can also look at it through this lens of some external work multiplied by some distance. And I just want to mention also that this is the simple case. This is kind of a simple version. Something you got to watch out for. I don't want to go too much into that in this video, but the reason why it's the simple case is that in this case, first of all, the direction of the force. So I'll put an arrow over there saying, hey, it is a vector. This external force has a direction, and the direction of the motion are the same. So we don't have to deal with that at all. And the second thing is that this force, it was constant. I won't go into how to deal with when those things are not the case. It's not too complicated. So when we're doing the unit on potential, just a reminder then that we can look at work as something that causes the change in energy, is the first one. And we can look also as that when we examine it closely, there's always some external force which is pushing through some displacement. Okay, thanks, and I'll see you in class.